Wonderful. Well, welcome back. I am very excited because this next talk is going to be a joint talk. So with a great joy, I'm going to be introducing Lovro and Sung-Shik, who are going to tell us about Klor. Now, has anybody heard of it? Okay, cool. Couple fans.
One person.
What's that?
One person has.
Yeah, what? No, I saw another hand over here.
Oh, okay.
A couple hands, actually. Okay, well, I'm not going to keep the stage anymore. I'm very excited because we're about to learn so much right now. So please give it up for our two wonderful speakers.
Okay, thank you for the introduction. Hello, everyone. I hope you're enjoying the conference so far. We definitely are. Thank you so much for joining the session here today. We have been working on a project over the past year to make it possible to do choreographic programming in Clojure, whatever that means. And so we are really excited to tell you all about this project this afternoon. We are, as stated, with two people. Lovro, he's sitting here. He's the lead developer of the project. So he's the more important person, I would say. Myself, I think of myself more like the janitor, really. So I pick up all the non-technical slack, do the administrative stuff. But at heart, I'm also a developer. So I do have a fair understanding of what the project technically is about. So the plan for today is I will first take a few minutes to explain what the project is about and why it's useful. And then Lovro will take over and he will he will explain how the project can be used. And so we'll do a little bit of live coding, give a demonstration, just to give you all an impression. Okay. All right. So for safety, I'm going to assume that nobody in the audience actually knows what choreographic programming is. I think that's a safe assumption. In fact, the Heart of Clojure organization, when they announced our talk on the website, on their blog, they write, "We will be honest, we had not heard of choreographic programming before, but this is a talk with strange loop vibes." So, I mean, whether you're depending on whether you're an optimist or a pessimist or a realist, this could either be like a compliment, an insult, or a threat, or all three things at the same time. We really don't know, but we are here, right? And so we will try to conjure up some of those strange loop vibes during this talk. Okay, well, all jokes aside, against this background that nobody knows what choreographic programming is, I will start with choreographic programming 101, so to speak. So let's forget about Klor, forget about Clojure for now, and well, let's first have a look at that. So in the tiniest nutshell, I think choreographic programming is about programming of choreographies, right? Just to give you a self-referential definition. But that by itself could mean one of two things. Right? It could be about a domain-specific language to express dance notation as programs. Right? So we have like a digital version of the notation that you see here on the slide. And so in Clojure, we could imagine having a bunch of macros to piece together dance movements, and maybe we can compile them and run them, simulate them, perhaps even deploy on humanoid robots that can go through all the movements. That would all be kind of cool. But unfortunately, that's not our form of choreographic programming. So that's not what we're going to talk about today. Instead, when I, let's say, dream of choreographic programming, my dreams look something like this, really. So you have a bunch of academic papers written by computer scientists in programming language research, where they use this concept of choreography basically as a, well, as a metaphor, as a programming abstraction. Now, I imagine, I mean, my dreams, they do look a little bit underwhelming, I would say, especially as you guys were promised, you know, strange loop vibes, but we're only like a few minutes into the talk, right? So maybe that can still come. Anyway, these papers, academic papers, in general, I think academic papers, they're great. I read lots of them, wrote a few of them myself as well, actually. But these papers on choreographic programming, they tend to be a bit theoretical. And when I say a bit, I actually mean a lot. So when you browse through those papers, right, you will see many pages that look something like this. Now, I don't want to go into all the details, but essentially, you'll have lots of fascinating mathematical models, really, but at the end of the day, zero practical impact in industry. right? So it's the typical ivory tower science, I would say. Now, I realize that this is kind of harsh criticism of people that are supposedly, very smart, like professors and PhDs and so on. But I do actually feel quite comfortable to express all that, because as it turns out, Lovro and myself, we are among those people. We are among those academics. So we didn't invent choreographic programming, but we definitely used or misused, if you will, lots of taxpayers' money on doing research in this area. So Lovro, for instance, he got his PhD on choreographic programming earlier this year. And myself, I now need to confess, I suppose, that I actually wrote this page, this horrible page you've been seeing so far. I mean, there's no escaping that. I really did that at some point in my life. But the good news is, in the project we're presenting today, things are very different, right? For two reasons. First, this project is conducted completely outside of universities. Okay, so we're completely independent of any academic institutes, which already tells you something. And second, the primary aim of this project is to take all this, research and these academic papers and to turn it into something that's actually useful. Right, so we want to build the first choreographic programming framework that you can use even if you don't have a PhD in choreography programming like Lovro does. Right, so that's sort of what we're really shooting for. Now, I mentioned that we're doing this outside universities, okay, but that doesn't mean that we're alone. Okay, we have been working under the umbrella, so to speak, of what is called the Next Generation Internet Program. And this is like a huge funding initiative by the European Commission that aims to develop new core technology for the future internet. And I think we have been very lucky to have received a small slice of this funding cake. I won't bore you with all the the administrative details of how to acquire this kind of funding. This is like one of the administrative chores I had the privilege of doing. But what is the important thing right now? Right, the key observation is that somehow all these academic papers and choreographic programming, blah, 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 this is somehow related to the internet. And so what I want to do in the rest of my part of this presentation is explain a little bit more the metaphor of these choreographies, explain how this is related to the internet, and also show you some choreographic code, right? So we now finally get to the part where I explain what choreographic programming is. So forget about these papers for now, and let's just imagine that we need to build some application that runs on the internet, okay? I want to go through some of the ingredients that we need. And the first very important ingredient that we need is, of course, the machines, right? So we'll assume we have a bunch of machines that perform distributed computation to deliver function, whatever that function is. Now, in my example, I'm going to assume we have 3 machines, and I'm going to call them Alice, Bob, and Carol, just for simplicity. Now, metaphorically speaking, we can think of those machines as dancers, right? So these dancers, the computation, between quotes, that they perform is like movement in synchrony, right? And the function, again, between quotes, that they deliver is just aesthetics, right? Dance being an art form. Now, these machines, they don't exist in the void, do they? Right? They're connected to each other through a network of channels. And I'll call these channels in my example X, Y, and Z. And this network, it sort of provides the essential infrastructure that the machines need, right, to perform this distributed computation. And so metaphorically speaking, right, we can think of this network as the stage. Because in the same way, the stage offers the essential infrastructures used by the dancers to perform their movement in synchrony, okay? Then at runtime, when we execute the system, right, each of the machines individually executes a so-called local program that defines exactly what that machine needs to do. Right? So for instance, in this example, we could have for Alice that she first sends value 5 through channel X to Bob, and then later she receives a value through channel Y from Carol, and then she prints that value, for instance, just a simple example. And Bob and Carol, they do something similar. Okay? Again, metaphorically speaking, right, we can think of the execution of those local programs by the machines as the dancers actually performing their dance, right? Individual movement, but hopefully in collective synchrony, okay? Now, so we have now seen 3 correspondences, really, between distributed computation and dance, okay? Now, when we implement distributed computation, right, normally what we do is we do it very much from the perspective of the individual machines, right? So we write a local program for Alice, then for Bob, then for Carol. We put them together, we execute them, and really we pray, right, that they are actually compatible with each other, which often they are not, and then we need to engage in lots of, painful integration testing to make sure that everything's right. Now, interestingly, despite the 3 correspondences we've seen so far already, dance does not have compatibility issues like this. And the reason why dance doesn't have that is because dance has choreographies. Okay? Choreographies, they prescribe from sort of a holistic viewpoint what each dancer needs to do at which point in time, which particular movements, right? But not from the local perspectives of the individuals, but from the global perspective of the collective. And so, if each of the dancers complies with the choreography, then by design, it is impossible for any of the dancers to be incompliant or incompatible with any of the other dancers, simply because you cannot express that in the choreography. And so the whole idea of choreographic programming, right, is to provide linguistic support for programming abstractions that are similar in form and function to choreographies. Right? We program systems from this global viewpoint to eliminate local incompatibilities. Now, normally, when I want to emphasize, let's say, the technical nature of our choreographies, I will call them global programs. But more often than that, I will just say choreography. And here's the first example of one such a choreography. The details don't really matter right now. This is actually written using Klor, and so Lovro will tell you all about that in a few minutes. There are 2 more high-level observations I want to make. First one is that this single piece of code comprehensively prescribes the behavior of each of Alice, Bob, and Carol, right? Both computation and communication aspect, but it's only a single piece of code, right? And this is exactly this, global perspective that I've been talking about so far. Okay. Second observation I want to make is that this single piece of code, very important, it very much looks sequential, doesn't it? But it is not. And the reason why it's not is that before we execute this, we do a little bit of macro expansion. And so essentially what we have is a small compiler for these kinds of global programs implemented, as a set of macros in Clojure. And what this compiler does is it extracts automatically from this global program for each machine in the system a local program that prescribes exactly what that machine needs to do to comply with the choreography. Right? Now, this operation in these academic papers, it's called projection. So the compiler is set to project the global program onto your machines, and then you get those local programs. Now, before, I was criticizing a bit these academic papers and so on. But as it turns out, these fascinating mathematical models, they provide a foundation for choreographic programming that guarantees a bunch of very nice safety properties. And these safety properties, they include absence of deadlocks and absence of communication errors. In other words, the only thing you as a programmer need to do really is write this global program, you click on a button, you automatically get these local programs that you can actually deploy, and you can be sure, because by construction the machines will be compatible with each other, you do not have deadlocks or communication errors. So that would be, I think, the main advantage of applying this approach. Okay, so this is the tiniest nutshell I could find to explain in 5 minutes what this is about. I think this concludes my part of the presentation. At the end of the day, I think what I tried to do really was sell you religion, right? And now Lovro, he will continue and sell you the Bible.
Sung?
Oh, I need to take my laptop to the right.
All right. Thank you, Sung, for the how and the what. Now we go on to the, for the what and the why. Now we go on to the how. So for this thing, we're going to be running a little demo, and we'll follow a repository that I set up. You can find it on GitHub under lovro.stu/Klor HoC demo. So those of you that want to follow along, you can just go there, you git clone the repo, and you jack in with your favorite editor, and everything should just work, hopefully. So that's what I'll be following, and we'll see Sung setting it up just now, so you can also follow with us. So you clone the repo, and he's just going to get his editor set up in the meantime. All right, synchronously, I will go on to actually show you some examples. So Sung talked about this idea of a choreography, which is a global program, and about this idea of projection. So the main idea of Klor is basically, let's do projection with a macro. So our main entry point over here is going to be the def core macro, so define a choreography. And the syntax is very similar to that of defn. But there are two new components over here. So we have these two things. The first one is what I call a role vector. And the second one is the choreographic type. And I'll explain what this means in a second. So in a choreography, we know in advance the participants, the number of participants, and the participants, we give them names that are actually, dancing in this choreography. So that's the role vector. The role vector serves to introduce our participants. So we say in this choreography, we have two roles, A and B. And then the second component, which is the type, is essentially an annotation for the Klor compiler that tells Klor what the interface of this choreography is. The types do not restrict the structure of the data itself, so we are not concerned with whether it's a string, whether it's an integer, whatever. We're interested in where the data is located. So it's sort of a location type system, and it's been an interesting challenge to write a typed DSL that still provides sort of a REPL Lispy interactive experience, and I'll show you how all of this works. So here's a simple choreography. Like Sung said, the execution model is not sequential, so it's a concurrent execution model of all of the roles. So we call the participants A and B, we call them processes or roles, whichever name you want to use. And when reading a choreography, you really need to understand it in this fully concurrent setting. So each role executes fully concurrently, independently of the other role. So in this example, I think the best thing to show you is to demonstrate how this projection procedure works, and I'm just going to do that by macro expanding this form in my REPL. So we have this choreography above, which is just doing a print line hello world independently at A and B. And if you look at the projection, you can see how now this is a bit of implementation details, but if you squint, you'll see the point. You get a vector of functions, and each function is just the generated clojure code for the particular participant. So the first one is completely for A, the second one is completely for B. These are the projections. So the interface that you get when interfacing with Klor code is essentially you get this vector of functions, and we have some wrappers that work with this representation. But essentially, what is delivered to you after macro expansion are the projections, and then how you decide to actually schedule to execute them. Maybe you choose a thread, maybe a process, maybe it's on a node, maybe it's running somewhere else. You are in charge of actually hooking them up and making them talk to each other. And this is completely customizable, and we have like a whole system of we call them transports. So you could deploy it over TCP, you could do it completely in memory with core async. That's what I'll be showing today. We'll also have some TCP socket demos live, so let's pray that works. The final thing, I guess, to say in this example is, so this type that I mentioned, this specific types means this is a choreography, so the arrow is a choreography that takes 0 inputs and returns one thing at B. So that's the meaning of this type signature. As we go along, I'll show you some other type signatures and some other features of the type system that we have. So, okay, so how do I actually execute this? I have the projections. Okay, what do I do now? Well, instead of fiddling for the moment, we're not going to fiddle with, executing each projection independently for now. We're going to use Klor's simulator. So Klor comes with a built-in way to take choreography, take all of its projections, just run them on separate threads within the same clojure process, and they're all hooked up with core async channels. And this is very useful when you want to debug or you want to, do development while you're writing your choreography. So here's an example. We eval this choreography. So the macro expansion process is going to do all of the type checking and the projection. And now that we have the choreography, we can, let's say let's simulate it. So how does it look like? And you'll see the individual prints from A and B. And you'll also get a map of all of the results of the individual projections. You'll notice how B has a value, that's the 1, 2, 3 from the choreography, but A doesn't have a value. It instead uses this special marker from the Klor runtime, which is just a no-op. So essentially, if a choreography does not annotate, so if a choreography says that the interface, that its signature does not involve A in the return type, you're going to get this special value once you run the projection. And to demonstrate that this is actually, fully concurrent, if I execute it a few times, you can see how the order can be interleaved, right? So fully concurrent. Right, so how do you actually get anything done? Well, choreographies come with a specialized, so the main way they interact, the roles interact with one another is through communication, which is sort of a message passing kind of primitive. And this is the arrow you've seen from Sung's slide. So the single arrow over here means communicate from A to B, this value. And the fundamental idea of this operation is that it's effectively changing the choreographic type. It's almost like a location cast. So you start with something at A and you move it to B. And that's how you get things done. That's how you move things around. So in this simple choreography, we have now the type signature is a little bit different. It's taking a thing at A, and that's our parameter over here in the parameter vector. It's still returning a thing at B because the move, the move operation just moves it to B. So let's see how that looks in the simulator. So okay, if we're sending 42, you can see that the simulator shows us, all right, you moved from A to B. It's going to write down all of the communications that occur in the system. All right, so we have Klor, and once you do def core, you're sort of in this choreographic universe. Okay, what if how do you actually get work done? So how do you interact with clojure from Klor? So the way you do that is you just basically write standard clojure looking code. So here's an example where we have this remote invoke choreography, and it's going to take two components, but notice they're located at different locations. So F is going to be at B, that I'm going to call the server, and the value that I'm providing is going to be located at A, and I'll call this the client. So the choreography, sort of the global program, it's as if these two pieces are being provided independently, and then this global behavior occurs that's in the body. So what is going to happen? The client is first going to send its X to the server. The server is going to run the function F, and then on that result, it's just going to send it back to the client. And you can see this looks exactly, very, very neat, very clojure-y. There's not a lot of fluff in there. Again, we can evaluate this, and if I just run it with the inc function as an example, you get what we expect. I can also change it to dec. That works just as well. Okay, we can generalize the example a little bit. So, say, oh, okay, what if I have multiple arguments? What if I don't have just inc or dec? Well, okay, fine. We can just, let's apply it to a list of arguments. So we're using apply over here. And maybe I haven't called them by name, but these expressions of the form, B in parentheses or A in parentheses, these are what we call role expressions. And their purpose is to say, anything that is not already sort of annotated within this block, treated as if it's annotated with B. So this would mean, okay, the apply over here is sort of happening at B, but this does not restrict the rest of the body to also mention A. So it's not, sort of like an operation where you're constraining who you can mention. It's more of a syntactic help to say, within this context, don't bother me with annotations. Everything's going to be, everything that's not annotated is going to be at B. So in this case, the F is also at B, but the X's over here are at A, and Klor knows this. So regardless of this role expression over here, this communication is going to work just fine. So let's test it on the plus example. So we're sending over the arguments 1, 2, 3, and the server executes the addition and just sends it back. Right? So these are sort of the basics. Let's do something more interesting. Let's say, so maybe one thing to mention over here is that the server is the server already knows hard codes what function is being used. So if you look at the projection of this, for example, over here, so you can see what is the client doing. The client is doing a send followed by a receive, so it's waiting for the value. Meanwhile, the server is doing a receive from the client, applying the function, then sending back the result. But you can see the function F over here is sort of hard-coded, it's passed ahead of time. So let's have another example that we'll call remote procedure call RPC, where the client is the one that provides the name of the function to actually run. So what I'm going to do over here is now every component is located at A. So A is going to send both the name of the function and the list of arguments. It's going to send it to B, and B is just going to resolve that name as a var. right? It's going to get the var, and then with that function, it's just going to invoke the previous choreography that we had. This is where you can see, how do we start composing these things? So it works essentially the same as functional programming. So all choreographies are just functions and use standard invocation syntax. But one thing that's different is that you have to instantiate the role parameters. So in a way, all of the choreographies that you write in Klor, they are parametric on the roles. These are role parameters, and you could say they are location polymorphic. So before you invoke a choreography, you have to say who is playing which role. And you can permute these roles, in any way you want. The names are not significant. And it's kind of like if those of you who know, I don't know, like a functional programming language with static types such as Haskell, it's similar to the parametric polymorphism that you would find there with, generic types and similar. So let's have a look at this example. We have an RPC. And here's a function that I'm just going to call my plus. And I can do it in the simulator. But okay, this is nothing special. I'm just sending it to myself. Meanwhile, Sung has hopefully set up his copy. So we're going to run this example over TCP sockets, and we're actually networked right now on a VPN. So let's see if this goes as planned. But this time, instead of using the simulator, I actually have to invoke one of the Klor runtime functions, and that's the fundamental way you interact with the projections, which is play role. So play role means, here's the choreography, but I want to play a specific role of that choreography, and this is how you fundamentally invoke Klor from Clojure, right? So invoking Clojure from Klor is very simple. You just use it in the body of your dev core, that's fine. But when you want to do the opposite direction, now when it's time to schedule these projections, you do that with play role. Okay, so I have a little server over here. You can just kind of squint and see what's going on. So I have a little helper macro with server and with accepting connections, whatever. That's not too important. The important part is this play role part over here. And then Sung is going to have a similar play role part on his end. So I'll be running the server. I'm going to be B. I'll be the one resolving the var. And Sung is going to be the one sending the name and the arguments he wants evaluated. All right, so I start the server. And hopefully that works. And now Sung can go ahead, and I will switch to his view. He can go ahead and evaluate his client form. Yes.
So I will evaluate this with client.
There we go.
It works.
Wow, works over the VPN. Amazing. So Sung just sent me the name my plus, and he sent me the arguments, and my part resolved the name and gave him back the result. All right, let's say Sung wants to do it again, but I'm going to be sneaky and I'm going to change the plus over here to minus, and he's going to try and do it again. And let's see.
Can I go?
Yeah, you can go ahead. Oh no.
That's not right.
All right. Now Sung can cheat back, and he can also edit the my plus into a proper plus, and he can re-execute it.
See?
And he gets back the desired behavior. This is just to illustrate that Klor plays nicely with all of the Clojure dynamic redefinition features. So even though we have this, compilation pipeline little tool chain that's implemented on top of tools.analyzer, so those of you who know, that's actually like a little compilation framework. It's still, we try to be very, true to the nature of Lisp and true to the nature of Clojure and remain very dynamic. Now, this example might not maybe be very interesting because we're just redefining a defen. So, okay, that's all standard Clojure stuff. In a second, I'll show you actually redefining a def core, and that will also work as expected. So let's move on to our next example. And this is maybe where we introduce the big idea about Klor. So where do these types come into play? The types come into play once we start generalizing the idea of these locations. So not only can data be located at one location at a time, we can also have data that's located at multiple locations at a time. So what is the meaning of this? We call these agreement types, and here's an example of one. So this means here's a piece of data that's located at both A and B, and of course this physically cannot be the case, but what's happening behind the scenes is that Klor knows and tracks that the value held by A and B is equal. This is what it means, for them to agree on a value, and we represent this with an agreement type. The fundamental way you construct an agreement type, you cannot just, conjure it out of thin air. It has to be under some restrictions. The way you do it is with a double arrow operator. So the single arrow operator we saw before was just like a simple move. The double arrow operator is what we call a copy. And this actually preserves or sort of extends the value, shares the knowledge with another participant. So let's see just a quick example how this differs from what we've seen in the simulator. So if I execute the simple copy, everything, kind of the same. You still have the little print of the communication. But notice that the values returned by the projection are now equal. Meanwhile, in the previous case where we had the move, one of them actually didn't have a value. So this is the kind of stuff that Klor tracks. Now, why is this important? Why do you want to express agreement? Well, there's a fundamental sort of let's say issue with choreographies and conditionals, because what does it mean to have a conditional at the level of the choreography? So if one role decides on which branch to take, every other role has to be aware of this choice, to actually take the same branch, and so they would stay in sync. And the way we enforce this is through agreement types. So the fundamental rule is if you want to have a conditional, the guard of the conditional needs to be an agreement type. And the only roles that you can have in the body are then the roles that are part of this agreement type. Otherwise, it will not work. So here's a little example called maybe ink. And if I run it, depending on this outcome of this random coin toss, they're either going to, so either an integer is going to be exchanged and incremented, or we'll just print nothing. So if I execute it a few times, you'll see this non-deterministic behavior. Remote map I'll skip, but it sort of works the same way. We again have a condition over here, and they're trying to do a remote map procedure. So you have a list, and they're going to be exchanging these elements, and the server is going to be returning the results. But the same thing applies. And if I were to change this double arrow into a single arrow and trying to eval it, I would actually get an error, and Klor would report, ifs branches cannot mention roles not part of the condition, and it would tell you what's missing. So we've tried hard, to make these error messages, as descriptive as possible. Okay, let me close this. Right. That was an intro to sharing knowledge. Now we'll take a look at a little authentication example, which builds on this idea of agreement types. Here we go. So we have a little authentication example, and the idea is there are three roles. There's a client, there's a server, there's an authenticator, and the client is going to try to authenticate with the authenticator, and if that succeeds, the authenticator will let the server know, who will then send a token back to the client. So I'm not going to spend too much time on the details, but let's just see the example, and we'll run this over sockets again. So I've just started two servers. One is I'm running on my machine the server and the authenticator. Sung again is going to run the client, and he's just going to execute this client form over here. So
yep.
You can go ahead. Let's see. Yeah, and now you can type in the password. So the authentication example over here is going to, check whether his password matches this particular value. So you can go ahead and type in a random string.
Okay.
Right. Okay. Well, hurry up. All right. Let's redefine the secret to be secret haha with an extra A. Now Sung is going to try again. So the little example, you can keep going until you get it right. All right, so it's no longer secret as it was before, so the live redefinition of the def core really does work. So if he tries the secret haha now, that should work just fine. So he's going to try again. There we go. And he gets a token from the server. Right, so this is just to demonstrate that we've tried hard to make the REPL experience of Klor, really match that of Clojure. Okay, I'm going to speed run through some of these. Maybe I'm going to skip this one and just focus on... Right, I'll just quickly say something about higher order features of Klor. So we have choreographies as values, just like Clojure has functions of values. Functions as values. But there's a little, wrench in this whole thing, which is this little pipe operator over here with the function types. It's the higher order features in the choreographic setting are not as simple as those in just pure functional programming. I'll leave it to you to read the tutorial that we've set up, so you can go there and read about the details. But I'll skip to the last example that we have, which is just like a little toy implementation of tic-tac-toe. And you can see the choreography over here, and I'll just briefly skip through it. So we have, at the beginning, you know, A and B are playing together. A is going to be the currently playing player. And if we have a winner, okay, they both return the winner. But if we don't, then, okay, A is going to make a pick, and we're going to try to place the symbol on the board. And then we'll just take turns playing. All right, Sung, last example. You can execute your client. I've started the server.
Yep.
There we go. It's now asking me for input, so I'm going to say, okay, 1. You can see how the little position 1 changes to an X. Now Sung's going to do his move. All right, fine. I'll do 9. No, I'll do 7. Okay.
Oh, no.
And now I win. Oh, thank you. All right. So this is the main idea of Klor. So we have projection sort of as a macro expansion. Everything's running, you know, before the code is ever even loaded. This is the main idea. And if you want to learn more, you are free to go to our repository, lovro.stu/Klor on GitHub. And there we have sort of a little tutorial and also an in-depth reference that will guide you through what all of these types mean and, you know, how it works in depth. But thank you very much for your attention.